It's great to be perfect. It's great to be here to talk about who killed the PCB. And I'll just move ahead with this. We've got an inspector here, so Mark and I will play the role of the inspector and figure out who's killing our PCB. So most of you know MEN for a long time, but I will do a quick introduction of Ozen Engineering. We are the simulation experts of Silicon Valley, but we've expanded greatly. This year, in addition to California, you can see that Ozen Engineering has spread across up and down the east and the west coast of the United States. Different parts of the company has been around for a long time, but we have almost 40 years of simulation history now, starting from when ANSYS first started. We're supporting hundreds of companies on thousands of different projects, and because we're headquartered in Silicon Valley, the fate of PCB is all dear to our hearts. We care very much about electronics reliability, but also signal integrity and making electronics perform better and faster every day. So we have a very large and rapidly expanding engineering team, at least large compared to where we were a year ago, because we see that there's such an enormous demand and interest for using simulation to improve product development. We have a lot of expertise, but certainly we cover the full breadth of simulation, from multi-physics finite element analysis to computational fluid dynamics, high and low frequency electromagnetics. So that's a little bit about Ozen Engineering. And now we're going to look at the importance of, we're going to start with a couple of case studies of issues and troubles caused by PCB reliability. Then I'm going to talk about mechanical and thermal reliability, and I'll turn it over to Mark to cover the electrical side. So I think for the mechanical engineers in the room, what I say will probably be very obvious to you. And when Mark gets his turn, it's going to be very interesting to learn a lot. Every time I talk to Mark, I learn a great deal about simulation and the electrical side of things. So most of you probably have seen this, especially since this is the Santa Clara Silicon Valley chapter. PCB Assembly Failure Modes, the Air Force Avionics Integrity Program, this is many decades ago, did a study to look at why do PCBs fail? And the vast majority of PCBs fail due to thermal issues. There's a significant portion that fails due to vibration and humidity, and some due to dust. So what we take away from this is that it's important to address thermal, vibration, and humidity issues, and these can all be addressed using simulation. The vast majority of failures that we're seeing today are primarily due to thermal and vibration. So thermal cycling can cause solder joint failures. Vibration can cause solder joint failures. The shock can cause solder joint failures. So basically, when we're trying to connect different components together using solder, and this is a key area of failure. We're seeing this area become more and more important, as Amir mentioned. He's talking about larger boards, but boards have only gotten bigger. The packages have only gotten thinner, and boards are thicker now. So we have people doing, 36-layer boards and they want to attach the silicon directly, bare die onto the board, and it's the CTE mismatch is great. Silicons are very fragile and they're getting bigger. So the problem we face here is only getting more and more severe. We have stacked dies now. We have systems on chip, all kinds of technology that makes it harder and harder to ensure that you have the right life in your systems. What I'm really excited about is that over the last 10 years or so, ANSYS has gone to enormous extents to make modeling the reliability and the life of PCB assemblies much more efficient and much more easy to use. And this allows engineers to foresee issues during the design process, and really gives you a way to check things off, so that when you send that PCB to a thermal test chamber, when you put it on a shaker table, you have a fair amount of confidence that the system will survive. So let's look at a few of the troubles that PCB failure has caused. So there's an Air Asia flight that crashed in 2014. As was described in the Wall Street Journal, part of the issue comes from a cracked solder joint, which results in an electrical interruption that prompted the computer to generate warnings of a radar malfunction. So a warning signal isn't going to cause a crash in and of itself. However, this was enough of a distraction for the pilots that they missed other crucial factors. So this caused an airplane to crash. Everyone perished on board, and there are pictures of the specific cracks that occurred on the solder. This is just the most visible part of aircraft avionics failure. Avionics failure due to solder joint reliability. There are countless others, and they don't always result in crashes. Sometimes they require you to pull the PCB every 5 years instead of every 20 years. Sometimes it's big recalls, and sometimes people don't know, right? You don't know how severe a particular failure is. And we at Ozen Engineering have worked with all of these companies. These are real problems that companies have asked us, hey, something went wrong in our manufacturing process. Should we be pulling it out of every airplane, or can we do some testing? So we've had these discussions with real companies, company that says, hey, these components are supposed to last 20 years. We have 5 years of test data, and many of them are failing. We don't know why. So a little bit of simulation could help to address a lot of these potential issues. But more importantly, it also tells you what could be the issue here. Sometimes that's even more valuable. Many of us have seen was around when Xbox came around, and in this case, the head of Xbox hardware during the Xbox 360 era had this infamous issue where it's called the red ring of death. So basically, your Xbox at some point while you're playing the video game shows this symbol where it's a not quite complete circle, and this actually means that your Xbox is totally dead. You just paid, hundreds of dollars on a gaming system, and when this shows up, it means it's permanently failed. It's never going to turn on again. And this is happening all over the place for two Microsoft customers. It cost about $1.15 billion in repairs and lost sales. Huge issue. And you can see that the issue here was it occurred when the console reached a high level of heat. So it got hot because people were playing video games. Then it cooled off suddenly when the console was switched off. And all the mechanical engineers instantly know what happens when that happens, right? You have thermal expansion, suddenly it cools, and during the cooling, something got popped off. So a lot of stress was placed on the internal components, and that caused this ring of death. So this actually shows you that this package here, some of the solder balls have failed. And you can see the mitigation that Xbox put in. They put these little plastic glue holders in to try to hold this package onto the board to try to prevent some of the solder cracking. And for those of you who have been in the Silicon Valley for a while, Microsoft got really intent on fixing this. NVIDIA is very intent on fixing these issues. The team that went on to fix these issues basically traveled around the Silicon Valley to different companies fixing this exact issue, because during this time, we have very high performing microprocessors that generates a lot of heat, and every single one of them have these issues. Huge, not quite as catastrophic as obviously an airplane crashing, but a huge impact to the company, and obviously such an impact that many companies were willing to spend considerable amount of money to ensure that this does not happen. More recently, Mark pointed out that there was a U.S. safety agency discussed Tesla's camera issues. Now, we don't know if this was due to solder joint reliability, but it's a failure where after a few years, the repeater cameras on the Tesla model stopped functioning. They just give out. So we don't know what happened. It's electronics failure. One day, I'm sure we'll get to the details of this, but this is another case where potentially you could have a recall that would be quite costly to the company. So some really good examples of when electronics PCBs fail. And we're going to dig into what killed these PCB. And to be honest, the mechanical side is pretty straightforward. We have a package on top of a PCB. You put it in a car, it shakes around. You put it in an airplane, it heats up and shakes around. You put it in an Xbox, it heats up and cools down. So all of those things will result in the connectors failing. So it's like, that's typically the location where failures occur. And by connectors, I mean solder balls. So PCBs are typically connected to boards using solder balls. Different types of interconnects are available, but solder fatigue failure is pretty common. It's becoming more common recently, but probably within the last 10 years, ever since we moved away from leaded solder to lead-free solder, the solder balls have become much stiffer. They tend to exhibit different properties of thermal expansion coefficients, and they sometimes crack when you don't expect it to. So, but it's been a few years. I think most of the industry have moved on and figured out ways to ensure reliability, partly through simulation. So these are the three main modes of failure that we're going to talk about today. Mechanical shock analysis. This is a JDEC drop simulation where we put a very specialized strike surface down, drop an anvil with a PCB attached, and the goal is a 1500 G half millisecond half sine shock. So we can run that simulation and see what the stresses are on the solder ball, and that can be correlated to failure. A thermal cycling failure is when you put your board into a thermal cycling chamber and ramp the temperature up and down. And then by a PCB vibration, this will be a PSD spectrum where you put it into a testing environment and you want to see how long the system will last. This PCB assembly, PCBA, will last during the expected vibration testing environment. So, as Amir mentioned, people have been analyzing PCBs for a long time. And the key challenge of all PCBs is just how incredibly complex they are. And this is the key challenge when it comes to simulation, right? This PCB on my right-hand side has 11 layers, so it's not a very thick PCB. But if you look at every trace and every via as individual components, there's 21,000 bodies. So it's impossible for you to analyze every single one of these things in detail, right? This is a board. So just on this one PCB assembly, there are 585 components. And on one chip itself, you can have 300, which is a small one, but you can have 1,000 solder joints on that one component. So the challenge of PCB simulation specifically, but typically generally simulation in general, is how do we bridge that vast difference in scale? How do we find out if one of these components, one of these solder balls will fail on a board of this size with this many components? So that's the challenge that simulation tools like ANSYS has been tackling over the last decade. How do we make this process more efficient? In addition, there's some complex materials with the solder itself. Solder failure has been correlated to viscoplastic creep behavior of the solder. But once we have the model in place, once we have the material properties, you have to model pretty carefully, but there's a well-known way to handle those. And I'm sure in the previous discussions that was discussed here. So let's start by looking at the PCB level. How do we capture just the right amount of detail? And I'm showing 4 different approaches here. 5 years ago, there's only one, homogenized lump model, right? You take a PCB, you figure out how much copper there is, how much FR4 there is, and you do a calculation for the equivalent material in the board, one layer. Now, if you want to get advanced, you can look at each layer. So there's copper layers, there's signal layers, there's dielectric layers. You can split the PCB up into multiple layers and have equivalent material properties on each of the layer. And that's what we've done for probably a couple of decades, I imagine, to do these type of simulations. Probably 10 years ago, maybe 8 years ago, ANSYS decided to implement this trace mapping method. And this was used by other companies. This technique was around, but it wasn't all that easy to use. But what ANSYS allows us to do now is to read in the ECAD layout as a ODB file or IPC file, or even a BRD file, etc. So we actually read in the full ElectroCAD. We mesh the board completely independent of the trace layout. But then for each element on the mesh, we can calculate the amount of copper on that element. So rather than doing a lumped material on the entire board, we're going element by element across this board and calculating how much copper there is. And we calculate the equivalent material property for the orthotropic elasticity, thermal expansion coefficient, heat transfer coefficient, and everything else we need to calculate. So we get that data, then we map it together so that at each element there's a slightly different material depending on how much copper there is versus how much FR4. So this allows us to start to capture at our, as much detail as we desire. If we want to make this board resolve down to a micron in size, we can do that. If we want to do a millimeter in size in elements, we can do that. So we can pick and choose how much detail to resolve, and it gives us much better heat transfer predictions. It gives us much better stiffness predictions. We've had people that have giant blocks of copper on different, on just slabs on the board, and it behaves completely differently than if you smear them out. So this started to add a lot of interesting capability for us. So we're very excited to have this capability. And then just recently, probably 3 to 4 years in the past, we started looking at reinforcements. And this really resulted from the vast increased use of flexible PCBs. So in the flex PCB, the failure often happens into the copper interconnect because you're bending these things. But how do you actually model that efficiently and integrate that with FR4 or the polymer that you surround it with? So in the reinforcement method, instead of modeling, we actually model the traces as shell elements, and they're just overlapping and embedded in the solid polymer or dielectric element. And we pass so they're embedded, and this allows us to actually capture the stresses on the surfaces, on these traces, as well as the VS. And that gives us, allows us to predict whether traces and VS will fail instead of whether components on the board will fail. So I would say trace mapping is really for the BGAs and the components on the board, but reinforcement allows you to actually get down to the details of the PCB and see if the internal VS and traces will fail. So another big advancement for slightly different application. And finally, there's a full trace modeling approach where we model each of the traces and VS as a full 3D solid component. It's almost impossible to get this to work for any realistic PCB these days. I don't think I've ever tried to model anything real with that methodology, but I mean, it's theoretically possible. So really the three here on the left-hand side are what's used most common. And you can see that there's a rough graph of speed versus accuracy. And we feel like the trace reinforcement approach gives us very high accuracy comparable to modeling the traces themselves. But it is much slower than if we do the other two approaches. So different techniques for different applications. And you can use this for all kinds of failures. So this can be applied to solder reflow. So that's we've had, I guess, I would say 4 years ago, a lot of companies came to us to talk about solder reflow failures. When they put their board in the oven, it comes out and some of the components aren't connected. So just that reflow process itself will damage a lot of components or cause failure to connect. So by predicting exactly how the traces are laid out in the board, the warpage of the board can be modeled accurately, and that tells us particular areas where a reflow process may fail. We can do drop or shock simulations like a tumble test or the standard IPC analysis, shock and vibe for random vibrations, drop simulation, moisture effects, moisture diffusion to prevent popcorning, as well as thermal cycling. So this is your standard Darboux method for BGA solder joint reliability. So a lot of different things we can model. Once we're able to capture the components on a PCBA as well as the board well, I mean, we have all the physics needed to capture all of these different scenarios. So the trouble has always been how much detail and how accurately can we model a PCB assembly. But how do we go from simulation to reliability, right? Simulation gives you data. Hey, one piece of data, the board deforms by 2 millimeters, or the stress is at 300 megapascals. But as all of us mechanical engineers know, in order to actually go from that information to reliability data, we actually need to have reliability data. And that's another huge advance has made over the last just 3 years. We now have a full set of historical reliability data from testing. So depending on the type of package, the type of solder joint, the size of the solder joint, we're able to translate the deformation experienced on a board, for example, during a shock or random vibe analysis, and predict how long we take that deformation, we compare it to the vast library of data we have on durability and reliability. And from that, we can predict reliability of your particular component. So now it's possible to load in a full board with 500 components, and we can try to predict which component will fail first and how long that will be. And we can do a Weibull analysis to look at the percentage of reliability. In 20 years, are you going to have 5% reliability, 5% failure, 10% failure, or 1% failure? Obviously, we're very conservative in our calculations, so this typically greatly underpredicts the life, overpredicts the possibility of failure. So, for example, we had customers that came to us and say, "Hey, we're going through thermal cycling tests, and we need less than 0.5% failure on our system." So we did analysis. We made sure it was under this, and they said, "Oh yeah, we put it in the oven. It's 10 times as long." So, which is kind of order of magnitude is where we want to be. This is not going to replace physical testing, but it will give you a ton of confidence when you do physical testing to know that your system will survive.
You're gonna pass, yeah.
Yeah.
Excuse me. So you will use historical reliability data of each component, not specific to any part, right?
Well, it's packaging styles. There's DIMMs, there's DIPs, there's VGA. So there's historical data of all of these components, and there's a standard solder joint reliability calculation, very detailed analysis, but there's also looser empirical calculations and calculators we have. So that's all rolled together in the reliability calculation tool now. So we can do thermal cycling, we can do shock and vibe, and even like anode filament and via cracking, all of that stuff. So that's a lot of the vibration side, you have to do full finite element. But for a quick scan of thermal cycling, for example, we don't use a full finite element simulation. We just look at the relative thermal expansion coefficient, the size of the package, the size of the joints, the material of the joint, the PCB material. Take all of that into account, do some empirical calculations compared to the data we have, and we can estimate, I would say, a reliability prediction. But that's the only way you can scan a full PCB, right, for a few hundred components.
Okay. We'll have questions later. I have a question. Just I'm interested. Yeah.
Okay. I'm glad you asked. Absolutely. So that's the mechanical side. The thermal reliability has similar challenges. Again, I think this is kind of fundamental to all simulation. We're always dealing with vast difference in scale, right? A chip or die could have a single hotspot that overheats, and that can cause performance issues, can cause failure issues. But the environment of that die is important. So you look at the package, you look at the board, you look at the backplane, the system, all the way to the full data center. So again, the failure is important. And what we do is we typically divide and conquer, right? There are people that focus on package engineering. There are people that focus on kind of system level and board level engineering. And then there are people that focus on data center simulations. And you kind of tell each other that these are the bounding blocks. These are my requirements. You got to make sure you put my system in what the environment I expect, and it'll survive. And it's working out pretty well. But thermal analysis is required across this entire span of design. So on the package reliability side, we can model a detailed JDEC thermal chamber. And again, this shows you the ability to simplify the model for larger and larger scales. You don't want to model a data center with every package fully defined. So there is an option to model a detailed thermal model. We can use a compact thermal model. We can use a network thermal model. And these gives us junction temperatures, right? All of these methods gives us junction temperatures, but a network thermal model allows us to integrate the simulation into a full system or a very large environment, whereas detailed thermal models allow us to calculate what this network thermal model is. So rather than testing to figure out where your theta JA, theta JC, Theta JB network models, we can, through simulation, calculate that for you, and then you can integrate that into the larger assemblies for system level simulation. Just like I talked about on the mechanical side, the PCB thermal reliability, the effect of traces can sometimes be even more important in thermal analysis than they are in a structural analysis. And that's because these days, as the package is closer and closer to the board, some designers are starting to use the trace layout as a way to dissipate the heat. You know, you can dissipate it through the top of the package through heat sinks, but sometimes you don't have enough room for heat sinks. So you're trying to push heat into a big metal trace area, and hopefully that helps you dissipate the heat. So exact same concept applies here. We mesh a PCB using standardized meshing, and we calculate the amount of copper at each location. So there is a different, this is an orthotropic conduction value. So the conductivity in different directions are all different. And then this will be a dielectric layer where you see the little blue dots, those are vias going through the board. And we all know people are putting thermal vias on under packages to try to pump more heat through certain areas. So engineers get very creative, and it's up to the tools to keep up. Trace layout can affect the component temperature, and joule heating inside the PCB can actually be pretty significant. I was visiting some electronic testing companies, and they tell me that in order for their system to work, you need two 240-volt plugs to plug in to the wall, because they're going to pump over a kilowatt of power through their system, and a lot of that power is going to run through the PCB. So you imagine trying to run hundreds of watts through the PCB. The joule heating, just the squeezing the current through the PCB itself, causes significant enough heat that you'd want to include that in a thermal simulation. And Mark will talk about that in more
thermal
detail.
Losses, yeah.
Mm-hmm. And when you look at an electronic system, there's often fans and heat sinks, so lots of air moving around, and that often needs to be included as well in order to get realistic dissipation values. So when it comes to electronic systems, we look at the system level. We can model pretty much any geometry. We're doing a lot of analysis of motors these days, because electric motors are very popular in cars and airplanes, drones. But the bread and butter is kind of full electronic boxes, making sure that your CPUs don't overheat when you're playing the latest Xbox game or something. So the tools are there on the thermal side to tackle any geometry, any complexity, almost any physics. And the idea of complexity is that we have a lot of tools, a lot of models available to simplify things so that they're easy to analyze, right? We have full models for crack units and CPU racks, so we don't need to model all of the details. And that allows thermal engineers at every level, from the die to package to PCB to system to full data center, to efficiently work with each other to ensure that all the electronics don't overheat, provided you do a good amount of simulation. So that's it for my thermal and mechanical presentation. I'll turn it over to Mark Jones. He's going to talk about the electrical side, but I'll stick around. We'll have a nice Q&A session afterwards.
Great, thanks. That was great.
Oh, thank you.
Yeah, thanks, Mingyao. Let's see if I can. You guys see my screen, okay?
Yep, we can see it, Mark.
All right. Yep, so I will continue on from there. That was great information. I appreciate that, Mingyao. And I think, from the electrical side, I always learn a lot when I hear mechanical engineers talk. So it's an honor to be with you guys tonight and to be talking about the teamwork that we have. And so that's what this first bullet that I want to make. And this first point is really, this is a team sport, right? So we have electrical reliability concerns, but they're very much intertwined with the thermal issues that Mingyao brought out, and then earlier the mechanical issues he was talking about addressing. And so it's really best, in a lot of cases, if we work together very closely and communication is key to overcoming some of these really interrelated, interdependent types of challenges. And so we feel very strongly that that is best addressed using like a simulation-based design approach. And overall, working to the design requirements that are being handed down from the system level to the board, working together to make sure we minimize the number of physical prototypes that we have to make. Physical prototyping is expensive and it takes a lot of time traditionally to test and evaluate the performance. So we really want to work hard on the upfront side to make sure we can identify any issues in these areas and not kill the PCB right away, right? Killing the PCB right away would be just scrapping the prototype because it doesn't meet either the electrical performance requirements or some other issues on the thermal and mechanical side. And so a lot of people may look at a circuit board and they think, oh, this is an electrical problem. It looks like a lot of electrical components and, green or blue solder mask. It looks like an electrical engineering problem, but we all know it has a lot of mechanical and thermal engineering challenges as well. And so as you see this example here, there's a lot going on with this board, but fundamentally a printed circuit board is providing two complementary features here. It's supporting mechanically all of the components and the connectors that have to be used in the board. And it's also providing electrical connections to power the active circuitry and also to support data transmission between all the components that are on the board, whether that's a high-speed microprocessor or USB or RF microwave signals going on the board. And so really the entire assembly, the PCB assembly, can be very complicated, active and passive components, connectors that is attaching this board to the rest of the system for connectivity, housings and enclosures that help protect the board, as well as, like Ming Yao mentioned, thermal issues, fans, active and passive cooling. So it's a nice design problem to be working on. It's nice to hear some of the history Mira was talking about, working over the decades with the boards. And so in general, the printed circuit board construction, fabrication methods, I'll talk a little bit about that, but there's different types. We'll talk about multi-layer boards. The 6-layer board you see on this example is very typical. This can get very complicated very quickly, but what we want to focus on is just some key terms, and that's the stack up. So the stack up is the configuration of the board. So it's made from a laminated stack up of conducting materials, usually copper, and then a dielectric material. We mentioned FR4, very popular, and then maybe alternate materials that support higher speeds and higher and lower losses. But that stack up is a very important part of defining the board and how it's going to perform, both from the mechanical standpoint as well as the electrical standpoint. On the metal layers, we have traces that route between all the components for the connectivity. We have large planes that are used for implementing like low impedance structures for the ground nets or the power distribution system. And then we have very important pieces called vias, and these are vertical interconnects. These go between the layers, either all the way through the board, plated through holes, or between an inner layer and an outer layer. There's different configurations of those, but these are very important to manage from both mechanical, thermal, and electrical sides. And then the last term here we have is just the nets. If you've heard someone talk about a net, electrical engineers talk about electrically connected pathways on the board. So whether that's connecting signal, flow, or either the distribution of power. And what we've seen over time, over the years, we've seen the PCB designs get more complicated, definitely more compact, more dense. And this has really enabled the widespread adoption of the printed circuit board in many industries, many applications. They're all around us, everything we do. I'm sitting here with a smartphone, we have everything, smart speakers, cars. And so today's vehicle is a good example. Today's vehicle has about 30 different digital systems involved. And according to IEEE, the cost of those systems is climbing a lot and is actually at around 35 to 50% of the total car cost. So this is a very important topic that we're talking about. But back in the beginning, many years ago, it was not as complicated a problem. There were single layer boards and through hole components, leaded components. very low speed signals traveling around, so it was not as complicated. But over time, the technology got more advanced, and we moved on to multiple layers, which carry a lot of advantages for signal routing, for coupling, just for density. There's a lot of advantages to that, and about 90% of boards today are built for multiple layers, and so it's very common. It's basically taken over the industry, but we moved on even from that with manufacturing advances and material development advances. We've moved into hybrid rigid flex assemblies, and you may have seen these. These are in flip phones. These are in all kinds of cool, televisions, all kinds of things that might have to move. They're very thin and flexible, and then they're attached to more of the standard rigid board. So we've got to deal with a lot of regulation as well. You may have heard of ROS, which stands for Reduction of Hazardous Substances, working with the environment and limits on the hazardous substances and making sure that the industry is compliant in those areas. That's a global adoption of that. So what we see today is really multiple layer, multifunction type of boards, whether they're RF, mixed signal, analog, digital. And this really kind of drives home the point that these engineering teams need to work together to solve these really interrelated challenges. So on the electrical side, what I'll focus on is just 3 areas. These are kind of interrelated, but they are distinct in ways, and the signal integrity, power integrity, and electromagnetic compatibility. And signal integrity is essentially concerned with the quality of the signal. And so making sure if it's a digital signal that we receive a 1 or a 0, if we transmitted a 1 or a 0, there's no corruption or contamination of that signal. On the power side, the power integrity is mainly interested in making sure that the quality of the power is delivered to all the active components is very stable. It's within the restrictions that we have for the requirements of the board components, and that it has no high frequency ripple or thermal issues happening because of hotspots on the board. So there's a lot there for the mechanical overlap of that and thermal overlap of power integrity. And then a very important piece is electromagnetic compatibility. All of these issues are electromagnetic at heart. Signal integrity and power integrity are related to electromagnetics. And then electromagnetic compatibility is essentially trying to control unintended radiation from the board, leakage or conducted emissions, things that would produce interference, maybe safety issues if it's in a medical environment. And so making sure that we don't produce those emissions, but also that we're not susceptible to other sources of interference. And so that's a very important part of this 3-legged stool. So in general, just from electroengineering, kind of a basic overview, if you're thinking of signal transmission on a PCB, one of the fundamental parameters that is important is called the rise time. And so if we have a digital signal, it goes from a 0 to a 1 in a certain amount of time. And over the years, this is getting faster and faster and faster. And so as this gets faster, data rates and quality of signal gets better in terms of technology, but the challenges get harder because the bandwidth that's occupied by that signal on that edge rate is climbing gigahertz, above gigahertz. And so what that does to the interconnect problem is it makes the interconnects look electrically longer and longer so that we're managing the interconnects. And that's really the heart of signal integrity, is managing these interconnects between the components, kind of making them invisible. You want them to be a wire. If it was a DC voltage, it would just be a wire, but we're trying to minimize any reflections that happen. We're transmitting a signal. We know it's going to be a 1 coming out of the driver. We want it to be a 1 when it gets to the receiver, but along the way, there can be a lot of issues at these high speeds. And so really, at the heart of it, signal integrity is getting to be a harder problem because of what I just mentioned, because of the faster rise times we're seeing in the standards today, longer interconnects on bigger boards, higher frequencies on the clocks. And so if you think about signal integrity, some rules of thumb are just basically, if you're dealing with high-speed data signals, rise times on the order of 1 nanosecond or faster than that, then most of the board traces that you're going to have are over 1/10 of a wavelength long electrically. If you do the math and look at that, it's going to be more like an RF transmission line rather than a wire. And so that's going to prevent accurate transmission. It could lead to radiation. Coupling could lead to reflections. And so a couple of key topics here just to be aware of is if you have—
So the trace, excuse me, the trace length should be greater than 1/10 the wavelength. Is that you need to have it longer?
No, trace lengths
No.
that are greater than 1/10 of a wavelength are—
Is a problem.
Yeah, they're considered more like a transmission line.
Okay, yeah, that's what I meant. Yeah,
Yeah,
I understood it differently. I said, wait a minute, you don't want it to be longer. Okay, good, thanks.
yeah, good question. And if you have those trace links and they're not matched, right? If you have differential pairs that are essentially trying to transmit the same signal with the opposite phase, they need to be equal lengths. So that can lead to issues as well if you have circuitry that's really small and packed together tightly with closely spaced lines. That can really lead to coupling in certain parts of the board if you have parallel or coplanar lines. So there's a lot of things at play here, and I don't have time to go through them all, but there's a list. It's a huge topic of dealing with the signal integrity and EMI. And so I would like to just highlight some of the more common causes of degraded signals on the circuit board from the electrical standpoint. And the first that I'll mention is the obvious one. We have signal loss or attenuation due to that all-important stackup. And so we have dielectric loss versus frequency that increases. We have conductor surface roughness in the copper that increases versus frequency. As the board gets bigger and the tracks get longer, you have more loss. We also have reflections at interfaces, inhomogeneous interfaces there, transitions between layers, vias. Any transition along the line can lead to impedance mismatch. And this gets into some of the RF type of terminology where you're looking at 50 ohm transmission lines that are controlled impedance, and we try to design the vias so that they don't have reactive properties like capacitance and inductance. And so as these frequencies get higher, you start talking like that. The terminology becomes more of an RF domain. And then the last one I'll mention is very important, and that's obviously coupling, crosstalk between closely spaced lines, whether they're tracks on the board or it's a harness that's coming onto the board with wiring harnesses that's attached to the board. They can couple as well. And so EMI is essentially another form of noise. It's a signal that's undesired, and that's kind of the meaning of the word crosstalk, is another signal that's coupling onto your line. So the bit stream we've been talking about, say we have a perfect bit stream coming out of a transmitter or a driver. Because of all these issues in the signal integrity, we can get degraded performance on the other end of the line. So the receiver, we can have difficulty figuring out, is this supposed to be a 0? Is it supposed to be a 1? And that's what causes circuits to malfunction. And so we can have functionality issues with the circuitry. We can have reduced performance from the electrical standpoint. We can have intermittent problems that are hard to track down in practice. And so this is tied to this idea of signal integrity and making sure that the quality of the interconnects on the board are carefully managed. And one tool we have, you may have heard of this, but it's called an eye diagram. And so there's an eye diagram that's built from overlaying all of these transitions between zeros and ones. We can put that on one chart, and we can do this in simulation. We can do this in measurement. But on the x-axis, we have the timing of that. So we can look for timing issues. On the y-axis, we have the amplitude. We can look for noise issues or distortion. And this is a very common way, if you hear signal integrity engineers talking, they'll talk a lot about the eye diagram, the eye width and the eye height, the opening of the eye mass. There's a lot of terminology there. It's a great tool to really dive into issues that are happening. And so here's an eye diagram just for that. So as an example of a problem, this is a via that goes from the outside to the inside of the board. It's very common to have a plated through hole. And the question becomes, well, do I need to back drill that via? Is it going to cause a problem at the data rate I'm running at? And you see here simulations that show in the frequency domain, the time domain, the discontinuities caused by leaving that via stub there. It causes a resonance, it causes a capacitive discontinuity. and on the bit rate we're pushing through it, it can cause a violation of the eye mask. So up in the upper right, you can see that eye width closing as the stub is getting longer and longer. So these are issues that need to be managed on the electrical side. And another example I'll give you is on any given layer, if we have routing that needs to be carefully controlled, like these differential lines, and say we have a mechanical issue like a keep out region or a mounting hole location, something that's interrupting the pathway, there's a congested area of the board, you can start having issues routing those lines. And so as we separate those lines out and create asymmetry in the layout, we can lead to issues in the near field and the far field for radiated emissions. So in this example, we can see just this very simple asymmetry, a bent line in the trace, and right above the line, we can see a huge difference in the radiated emissions. And if we turn that into a 1 meter radiated emissions, which is equivalent to a test for compliance, there's a spike there around 600 megahertz that would cause the board to fail at that point. The board would not pass the qualification test. And so that kind of highlights at high speeds what the interconnects need to look like, and make sure that the mechanical team is involved and we have all the components grouped together. We have all of the parts of the team kind of informed about some of these issues. And so as we are developing that layout, we can start looking on the electrical side and make sure we evaluate any issues that would pop up and things that would need to be addressed, changes to the layout. And one of these is for crosstalk. We can pull in the layout that's proposed. We can identify any areas that are exceeding a certain amount of crosstalk. This is a very common thing to do, either in the frequency domain or the time domain. We can look at those voltages, see if they're exceeding our expectations and violations, and then we can just change the layout appropriately to make sure we don't have the coupling issues. While we have the layout in there, we can look at the impedance of the line, and the impedance of the line for controlled impedance lines needs to be very carefully managed, whether it's a differential line or a single-ended line. And we can set up thresholds that will allow us to see where on the board the impedance is having an issue. Maybe it's crossing over a split ground plane or some other issue, coupling to another place on the line, a nearby plane. So we can look for issues that would increase those reflections and reduce the signal transmission path. And then something else that I think mechanical engineers really know a lot about is resonances. And so these are sort of like, the eigenmode analysis. So we can pull in that layout and look at the power plane and the ground plane and the stack up, all the configurations, and see if at a certain frequency that we have a resonance that happens somewhere in the board, and we have an active component that's going to excite that resonance. And when you excite that resonance, just like when you do a modal analysis in the mechanical side of things, you can have, in this case, we can cause EMI. We may radiate more, or we may contaminate the power, the impedance plane. And so this is something we can reshape those areas. We can put decoupling capacitors in those areas. There's strategies you can do to minimize the effects of those modes. And then one more I'll mention on the power side. It's very important to control the impedance of the power distribution network. And as we're laying out the board, we're trying to get a very low impedance. In this example, it's like 1 ohm. So it's typically can be much lower than 1 ohm. But we do that by distributing decoupling capacitors around the board. And so with simulation, we can optimize the values of those capacitors, the locations of those capacitors, the cost of those capacitors, making sure that we meet the target, but we also do that with the optimum solution. And then, like Ming Yao mentioned earlier, there is a DCIR analysis that couples into the thermal side. We can set up our voltage sources all over the board. We can look at the current draw from each component. Once we have all of those defined, we can do an analysis that will give us the DC voltage drops, see if there's issues delivering the power to each component. If we're exceeding the voltage drop so that the component's not happy and it's not seeing a minimum voltage, that's a huge problem. So we can correct that. We can look for current crowding, current bottlenecks. These are things that we can reshape the part of the board to minimize those issues. And then as we take those results from the DC analysis, the power losses that come out of that are very important because those can be fed directly into the thermal analysis. And so you can see on the left-hand side here, we've got an iterative process where the power losses go over to the thermal solver. The solver uses those to produce a temperature distribution everywhere in the board. Like Ming Yao mentioned, this is joule heating. We can take those temperature distributions and update the material properties of the conductors and the dielectrics, and then we can rerun the DCIR analysis. And then we do that in an automated way until we get convergence. And then on the right, you can see what that leads to is an accurate distribution of the temperature throughout the board, so we can address hotspots. We can address any passive cooling, active cooling, anything we need to do, heat sinks, thermal vias, fans. We can work with the thermal problem, but we also can get a very accurate distribution for voltages to make sure that every component has the appropriate voltage that it needs for appropriate for functionality. And so in summary, I guess we asked the question, who killed the PCB? That's been the topic tonight. I think the evidence is saying from some of the studies that thermal issues are really a driver, right? It's a really key driver. About 50% problems can be traced back to thermal. It could be a hotspot, could be thermal cycling. It's a very important topic. And it's interrelated with the other two, especially the electrical side. But vibration and shock also have a huge impact on many boards. I've had engineers tell me that the board vibrates apart, basically. And so the stack up that the electrical engineers choose has implications in the structural domain. And then the third culprit that we could point the finger at would be the electrical side. Maybe the signal integrity problem was not solved appropriately, and we had EMI issues. We had malfunctioning circuitry, or we were susceptible to another source of interference. All that can lead to failures from the electrical side. But as Ming Yao mentioned, the failures, no matter how they're caused, they can have serious consequences in the real world. We can have safety issues. We can have cost overruns or product recalls, delayed schedules. And so none of those are anything we want to have anything to do with. But thankfully, in today's modern era, we have access to these integrated design and simulation workflows. And then these can allow us to identify any issues with the board even before we build a prototype. We can do this all in simulation. And the fact that I really like is we can couple these tools together from the electrical engineering side and the mechanical engineering side, and we can work together to avoid these types of errors. So the last thing I'll mention is that feel free to contact us if you are interested in learning more about this topic, about the capabilities of the ANSYS simulation software. We'd love to talk to you. If you have engineering challenges that you'd like us to get involved in, we have consulting services. And so you can reach us at info@ozeninc.com or the phone number you see there. And so with that, I'll thank you very much for your attention and your time tonight. And I'll turn it back over to Lexi and Isaac.